Coarser grains tend to drop out early as the river slows. Some fine particles are deposited on the delta, but most remain in suspension and travel well out into the Gulf. For the past 6,000 years, ever since sea level rose and stabilized after the Quaternary Ice Age ended, the Mississippi River has been building up its modern delta, first one lobe, then another, as accumulating sediments repeatedly divert the river's flow. So far, the river has created 7 of these deltaic lobes. Someday it will jump from its current channel and flow down the Atchafalaya River in a shorter, steeper route to create yet another lobe. If the river succeeds in switching to a different channel, as indeed it someday must, cities like Baton Rouge and New Orleans will no longer have river access. The U.S. Army Corps of Engineers is trying to prevent, or at least delay, this geologically inevitable event because of the staggering negative economic impact. People have moved up and down the Mississippi for hundreds, if not thousands of years. The river is famous for its iconic paddle wheel steamers, but those were displaced with the advent of diesel engines. Now towboats push 6-acre barges laden with fertilizer, grain, and coal, commerce that sustains the nation's midsection. The Mississippi is a working river. As America's most important waterway, it's been heavily manipulated. Above St. Louis, 42 locks and dams aid navigation, affect the flow, and trap the river sediment. Artificial levees have reduced the seasonally wetted floodplain area by 90%. Millions of people living along the Mississippi rely on treatment plants to make the water drinkable, even though it's been used and reused many times upstream. Fertilizers are flushed from farmers' fields and enter the river. These chemicals are carried downstream to the Gulf of Mexico, where they promote the growth of algae, which, when it dies, depletes oxygen. In this way, a 7,000 square mile hypoxic dead zone has been created off the coast of Louisiana and other Gulf states. With so much industry along the river and so much agriculture spread across its floodplain, pollution has to be managed and minimized. We ask a lot of this great river, and we've profoundly altered it in modern times, but it continues to shape the heart of this country. What did you learn? The Mississippi River's flow velocity is primarily controlled by gradient, discharge, channel roughness. Discharge controls the Mississippi River's flow velocity or speed. If you had to choose, which one of these stretches would you say is lower in the Colorado River basin, and why? Rapids on the Colorado River show that it's quickly losing elevation as it tumbles through Cataract Canyon in eastern Utah. By contrast, the river has a much lower gradient as it flows peacefully through the Imperial Wildlife Refuge on the western border of Arizona. Lower gradient can suggest that a river's mouth is close by.
The discharge of a river system changes over time because of variations in the amount of precipitation received by the drainage basin. Studies show that when discharge increases, the width, depth, and flow velocity of the channel all increase predictably. As we saw earlier, when the size of the channel increases, proportionally less water is in contact with the bed and banks of the channel. This reduces friction, which acts to retard the flow, resulting in an increase in the rate of stream flow. Monitoring stream flow. The U.S. Geological Survey maintains a network of about 7,500 stream gauging stations that collect basic data about the country's surface water resources, figure 16.12. Data collected include flow velocity, discharge, and river stage. Stage is the height of the water surface relative to a fixed reference point. This measurement is frequently reported by the media, especially when a river approaches or surpasses flood stage. Stream flow measurements are essential components of river models used to make flood forecasts and issue warnings. There are other applications as well. The data are used to make decisions related to water supply allocations, operation of wastewater treatment plants, design of highway bridges, and recreation activities. Figure 16.12 Stream gauging stations. The United States has a dense network of stream gauging stations. To determine a channel's discharge, it is necessary to survey the channel to determine its shape and calculate its area. A stilling well measures the stage, and a current meter determines flow velocity. Changes downstream. One useful way of studying a stream is to examine its longitudinal profile. Such a profile is simply a cross-sectional view of a stream from its source area, called the head, or headwaters, to its mouth, the point downstream where it empties into another water body, a river, a lake, or the ocean. Figure 16.13 shows that the most obvious feature of a typical longitudinal profile is its concave shape, a result of the decrease in slope that occurs from the headwaters to the mouth. In addition, local irregularities exist in the profiles of most streams. The flatter sections may be associated with lakes or reservoirs, and the steeper sections are sites of rapids or waterfalls. Figure 16.13 Longitudinal Profile. California's Kings River originates high in the Sierra Nevada and flows into the San Joaquin Valley. The change in slope observed on most stream profiles is usually accompanied by an increase in discharge and channel size, as well as a reduction in sediment particle size, figure 16.14. For example, data from successive gauging stations along most rivers show that, in humid regions, discharge increases toward the mouth. This should come as no surprise because, as we move downstream, more and more tributaries contribute water to the main channel. In the case of the Amazon, for example, about 1,000 tributaries join the main river along its 6,500-kilometer, 4,000-mile, course across South America. Smart figure 16.14 Channel changes from head to mouth. Although the gradient decreases toward the mouth of a stream, increases in discharge and channel size and decreases in roughness more than offset the decrease in slope. Consequently, flow velocity usually increases toward the mouth. Tutorial. Head to mouth. In order to accommodate the growing volume of water, channel size typically increases downstream as well. Recall that flow velocities are higher in large channels than in small channels. Furthermore, observations show a general decline in sediment size downstream, making the channel smoother and more efficient. Although the channel slope decreases, the gradient becomes less steep toward a stream's mouth, the flow velocity generally increases. This fact contradicts our intuitive assumptions of swift, narrow headwater streams and wide, placid rivers flowing across more subtle topography. Increases in channel size and discharge and decreases in channel roughness that occur downstream compensate for the decrease in slope, thereby making the stream more efficient, see figure 16.14. Thus, the average flow velocity is typically lower in headwater streams than in wide, placid appearing rivers. 16.3 Concept checks.